Okay, so as an introduction, let us take a look at the basic model we will discuss stability properties for. So we have a diffusion process X defined via this SDE here, driven by a standard Wiener process, and we have some drift function H and diffusion matrix sigma. And the parameter we are interested in our estimation problem will be this drift matrix capital A. Yeah, and the coefficient functions are given functions on the d-dimensional numbers. So a very common approach to perform this estimation is maximum likelihood, because for these class of diffusion processes, the corresponding Rado-Nikodym derivative is explicitly known for different parameter choices A as a function on the path space, so on the space of continuous functions. And then we obtain our estimator by maximizing this likelihood function here with respect to A. It's important, as I just said, for us that this likelihood function is in this form a function on the path space, and these stability properties we are investigating are in the sense that we would like to have continuity of this functional, our maximum likelihood estimator, let's say in supremum norm or some other norm on this path space. So why is this important? When we look at applications, we will never observe a full path of a process, but and we will only have approximations of a path available. And in addition, in many examples, we will have also measurement errors. So the real path that is underlying this phenomenon we are investigating is not known exactly. So, and this is the reason why continuity of this estimation functional is very important to us. Because otherwise, I mean, if we have a little measurement error in our data and this estimation mapping is not continuous, the resulting estimate can be very far away from what actually happened in the real dynamics. Okay. And we will also see later that these continuity properties, as an interesting side effect, also result in some robustness against misspecification of the model, but we will see that later on. Okay, so yeah, so I haven't mentioned yet. So in order to have an absolute continuous class of measures, we need that we have a non-degenerate diffusion part, then we have a well-defined maximum likelihood estimator, and then we find that the likelihood estimator here, A hat capital T, is in a solution of this equation here, where IT and ST are these two quantities down here. So yeah, so this is the general form. Let's look at a very simple example to motivate these stability questions. This is the Ornstein-Uhlenbeck process here, where we have a linear drift, A times xt times some constant diffusion coefficient sigma. And in the one-dimensional case, then we have a very simple maximum likelihood estimator down here, and this quantity S here then can be computed explicitly. It's just this term here. And we see immediately that in this form, all the quantities that appear in the estimator, they are continuous. Okay? They are continuous functions from the path space, they are continuous in sigma, and so on. But this situation changes immediately when we go to higher dimensions. So when the dimension of our process is greater or equal to 2, then we cannot calculate this functional ST explicitly anymore. And it's a well-known fact that these integrals here, when we have dimension d higher or equal to 2, they are discontinuous functionals on path space. And this causes stability properties of this estimator in higher dimensions. Okay, so just intuitively what I just already mentioned, what we would like to have is when we have two observation paths, x and x tilde, and they are close in some sense. So for example, they are close in supremum norm. We would like to have also that the corresponding estimates, they are close. And as we've just seen for the Ornstein-Uhlenbeck example, and this also holds for more general examples, we have continuity in dimension 1, but since these multiple integrals with respect to the diffusion process appear, this continuity breaks down when we go to higher dimensions, and this is a very problematic property because then the estimator becomes unstable in this sense. Okay, so how can we work around this problem? This is the point where rough path theory comes in. And before I speak about how we construct the stable version of this estimator, let's recap shortly what we need from rough path theory. So we have just found that in these maximum likelihood estimators appear these multiple integrals that have these stability problems. And rough path theory now gives us a way to define integrals with respect to Brownian motion or more generally diffusion processes in a pathwise sense that do not suffer from these stability properties. So when we have such an integral with respect to a diffusion process, let's say x, and we all know that when this process x has Hölder regularity that is larger than 1/2, then this can be defined in a classical way. But when we have, for example, the smoothness of a Brownian motion, then such integrals are not longer well defined, and such simple Riemann approximations are not possible anymore. So what now Terry Lyons did in his theory of rough path is he developed this approximation via Riemann sums one step further by adding second order terms and finding a suitable space, so the rough path space, and a suitable metric on the space in order to make such quantities here to converge, okay, and give meaning to these integrals even when this process x has less regularity than 1/2. Okay, so formally what is a rough path for us? So we have now regularity between 1/3 and 1/2, and then an alpha Hölder rough path is it's a path from 0t to the space R to the E, and also a second order object, which is this x, bold x here, which lives on 0t squared, satisfying this algebraic property, and with the property that both components fulfill this Hölder regularity, okay, for alpha.
What is R to the E? What is E?
It's just a dimension.
Why E?
I mean, yeah, it's a bit uncommon.
But it's not exponential of 1.
No.
In this literature, this is common.
Yeah, in this
It's always
literature,
interesting
they
to
use
see
E.
different conventions.
We use E in the statistical part, and you know.
So the next letter after E. Oh, now I see.
Okay, and when we have smooth rough path, so when these integrals here are well defined in a classical sense, then we can lift this smooth path to a rough path by just taking x and these integrals as second order objects. Yeah, and a rough path is called geometric if it is the limit of such smooth rough path in this alpha Hölder rough path method. Okay, and with this machinery, then Terry Lyons was able to construct so-called rough integrals for functions from C2 by setting the rough integral as the limit when the mesh goes to 0 of these linear approximations plus the second order terms. And when we have a bit more regularity, then he also defined what's the solution of such a rough differential equation. Okay, so why is this now useful for us? Because every continuous semi-martingale, for example, a diffusion process, can be lifted to such a rough path. And most important example, of course, is Brownian motion. So when B is a Brownian motion here, we can define the second order terms here, B bold, as just we can take the E2 integral or the Stratonovich integral, both choices are possible. And the Brownian motion together with these integrals then build a geometric alpha-Hilbert rough path. Okay. And then we can define what a rough differential equation is with this Brownian motion path, let's say. Okay, so here in this diagram we just see the steps of this construction. So we have the Brownian motion, we lift it to a rough path, and then we plug it into our rough differential equation and can solve this equation. And it's important here that this can be done in a pathwise sense. Okay, there's no L2 theory involved as, for example, in E2 theory.
Well, let me comment here. The second step is the pathwise one, right?
That's
because
true,
for the first step, for the lift, you need L2 theory, and this is where you have the discontinuity.
That's true. So how you get your second order terms, this is not fixed by rough path theory. This is what Christian just mentioned. And there you have to, either you choose your second order terms in some way, or you use some stochastic integral, which is of course uses some L2 theory. Okay.
But in your problem you observe x2, right? In the original problem. So how do you observe the second order term?
I mean, this is, I would say that the main question we are investigating now is this instability of these integrals that appear in the MLE, and how we can stabilize this object. And then rough path theory tells us that taking these iterated integrals, the second order terms, in addition, is the only way to have a stable or continuous mapping on the path space.
The only way?
Yeah.
Or one way?
No, it's essentially the only way. And I think it's a theoretical investigation because, as you know, we don't know the second order terms when we go to applications. Yeah.
So in some sense the message would be you should try to provide the second order term as part of the data.
Mm-hmm.
But how to do that?
This is the big question that people would like to know, and many people think about this. We have one example which is called a physical Brownian motion model, where you can make sense of this second order terms also in a physical way, it's not clear how to observe such quantities. But so the message is you need the second order terms in order to obtain a stable estimate. Okay, so going back now to the maximum likelihood setting for diffusion processes, we can now lift the diffusion process to such an alpha-Hilbert rough path, and then we can construct a new estimator on the space of rough path, which we call now here bold A hat T. And this is now an estimator from a rough path space D to RD cross D, so it gives you an estimated matrix. And this estimator has the nice property that almost surely it coincides with the classical maximum likelihood estimator. So this means that we have all the asymptotic properties that also the maximum likelihood estimator has. So we have consistency, we have the limit and normal distribution for the estimation error and also efficiency under some conditions, of course. Okay, so how does this stable version now look like? So the this quantity IT that we had before is the same as we had in the classical maximum likelihood estimator, but this these integrals with respect to the diffusion process that caused the discontinuity problems, they are now replaced by rough integrals, or more precisely by a Stratonovich integral with some correction term. Okay, as a nice side effect, we also see that when we look at the specification of this diffusion matrix, or we would say volatility in financial applications, then we also have now in general a continuous estimator with respect to sigma. So we can view this rough estimator A bold head as a mapping from the rough pathways across the space, this space of possible diffusion matrices, to our RD cross D should this be here, sorry. And this will also be a continuous mapping. This immediately comes out of our machinery. Okay, another nice property that I mentioned in the beginning already is this robustness against misspecification. So I think in many applications it's it's a difficult assumption that the driving process has independent increments. So people would like to have some dependence in the driving process, which is a Brownian motion in our case. So we know it has independent increments in the sense that we take now here WH to be a fractional Brownian motion, okay, which has some dependence in time, and this dependence is described by the Hurst parameter h between 0 and 1. Well, so when we look at the classical maximum likelihood estimator, for fractional Brownian motions, it's not so easy to construct integrals or stochastic integrals, and when the Hurst parameter is less than 1/2. So, I mean, there has been some work in this direction, but it's a nice property of the rough integrals that they also work for the fractional Brownian motion.
And h is bigger than 1/4 if you want.
Yeah, exactly. So we cannot go down to 0 with h, but there are some range where it's possible to define a rough integral.
So you substitute then the integrals that appear in AT, which were Stratonovich type integrals, by the alternative integrals for the fractional Brownian motion?
I showed you here this definition of the rough maximum likelihood estimator, and you can just use the solution X of this STE with driver fractional Brownian motion.
Where exactly do you plug in? So I don't see X bar on the right hand side of the equation. If we go back to the slide you were just on now. So where is X bar on the right hand side of ST?
Okay. It's hidden in this integral here. It's not written up.
In the first integral.
In this integral with respect to x, the dxs integral.
So this one you would then, in the fractional Brownian motion case, substitute with an adequate integral that works for a fractional Brownian motion.
Exactly, with the lift of the fractional Brownian motion to a rough path space.
Which would not be a Stratonovich integral based lift because that's not well defined.
So there you can use it. Yeah, you can use the Stratonovich.
Okay, so
It could be interpreted as a kind of Stratonovich integral because it has the same kind of change of variable formulas like Stratonovich, but of course it's fractional Brownian motion. It's not the Stratonovich integral.
So what is the problem then with taking the estimator right away and plugging in the fractional Brownian motion? So where does that break down? Why does the first lifting it and then applying the map to the lift?
So this is a different viewpoint. So in this misspecification part, I think the main message is that it's always better to use Stratonovich integrals. Because they are stable in several directions, where the E2 integral has problems.
So the AT of XH, this would involve E2 integrals.
Yes, exactly.
Okay,
the maximum likelihood, sorry, I didn't say that in the beginning. So the maximum likelihood estimator involves E2 integrals, and they have these stability problems.
But if H is small, then you need higher order, not just second order terms of the rough path.
Yes.
You need more information.
Okay, but we will now see some simulations where we see that what actually happens in practice. I mean, I will tell you later. Okay, so this is now just formally what we have just mentioned. So we can, from this fractional solution of our STE with fractional Brownian motion as a driving process, now construct a rough path, which I call here XH, and the corresponding estimator is then robust in the sense that when we have H close to 1/2, then the solution of the rough estimator is close to the estimate we get when we have the same dynamics with Brownian motion as a drive. Okay, so we have convergence when H tends to 1/2. Okay, so here's a numerical example where you see that this it's always a good idea to use these Stratonovich integrals because the stability seems to go much further than this convergence result tells us. So here I have simulated such an, okay, it's a one-dimensional STE, this is a simplification, but the point here is that we have first indices H which are very far away from 1/2, and we see that even for very short observation intervals and relatively few observations. So we see here the mean over 1,000 Monte Carlo iterations of our estimator and the standard deviation, and we see, I mean, even for such short time intervals, the estimator works very well. And I mean, this really stays stable over the whole range of first indices. I mean, which is very surprising to me. But I mean, I think the reason is that this Stratonovich integral doesn't have any stability problems that the E2 integral usually has. And when you use E2 integrals, this looks completely different. So when H goes away from 1/2, you see that the estimator really goes crazy, and this is what you see in this picture here. So when H goes away from 1/2, this is the Hurst parameter down here, and here we have the estimated variance of the estimator. So the blue line is the rough MLE, or the MLE with Stratonovich integrals, and the red line is when you use E2 integrals. I mean, and this is of course not a good idea because for when we have H away from 1/2, they are not defined. So what we get is an explosion of our estimate. And you see that also. But I mean, the point is, I wanted to see how fast this explosion happens when we have a discrete approximation of the integrals. Yeah. And also how the rough version performs.
So is this a discrete approximation?
Yes.
So if you, I mean, I'm a bit confused now. If you go to the limit, you would have variance infinity or something.
Everywhere.
Yeah, exactly. So I mean, with the smooth estimators, when we go away from 1/2, it immediately explodes. But for the discrete version, we see the explosion appears at a certain rate, and I think this rate is also known in theory. And here we see that. I mean, also for values close to 1/2, I think I think I had something like 200 data points in the simulation. on the time interval of length 1, I think. Yeah. And we see also close to 1/2 there is a considerable difference. Okay. Yeah.
Good.
Thank you.
Thank you.
Yeah, I think when you presented this in the Funky Friday session, Niklas asked the question which I still think is really interesting. Did you ever try to calculate two Stratonovich integrals? One where you take, I don't know, some discrete linear approximation of your observed data, and then you change the observation point slightly by epsilon, and take this part then, and then you look how far away those are, because you motivated this whole thing by linear approximations to the data.
Yeah,
and then you want stability, so you want to know that the lift is stable.
So this is the example we would really like to have. And so to construct really a sequence where we can see the discontinuity of this estimation map. And so we have discussed this problem, but it seems like it's not so easy to do it.
I assume it's technically involved to calculate integrals and see how it goes up.
Kind of challenging, so that's why we decided this is the next project. But this is really something the rough path community is working for.
You have to look for a smart perturbation of your convection that somehow translates nicely when you calculate the integrals.
And the point is, constructing some perturbation is not so difficult. This is okay, but we would like to have a perturbation which has some practical relevance.
Like different linear interpolations.
I think I haven't never talked in front of you about that, but when you have some path, it's easy to construct a version of this path or a sequence of paths which in the limit has a different second order term than this one by just here adding some circles.
Yeah, this you should.
You know this. Yeah, and then shrinking.
But that's not
circles.
relevant because you talked about linear interpolations.
Yeah, this is not relevant. And the question is, can we find some stochastic noise which produces a non-trivial second order term?
I just want to insist, I asked before, but of course, what you showed is that if I know the second order term, I can stabilize, but you didn't tell me so far that if I don't know, I cannot.
Yeah,
maybe there are other ways to stay in the classical context.
So this is a general result of Terry Lyons that you need the second order terms in order to have a stable mapping. So this is, I think,
for the rough path theory.
Yeah.
Not for your maximum likelihood.
So I think there is a theorem which says that there is no norm on the space of continuous function which makes them a Banach space such that the map from x to its integral is continuous or something like this.
So it's a property of the underlying stochastic integrals, and this is a general result that you need the second order terms to get a stable. This is what this is in rough path they call this equilibrium map that always gives you this motion.
This is stabilizing, but maybe there are other ways, not without rough paths, solving the problem in a stable way, like regularization, finalization.
That's true. If for instance, if you don't consider you have a whole path, but you have just discrete time observations, of course, it's stable.
Maybe it's actually raises my questions because comment. We have another ongoing project with Maxim Panov, unfortunately absent now. Could you show your original equation at the very beginning? So this one, that one. So you have dynamic of the process X, which is somehow dependent on unknown matrix or parameter T. And so if you don't observe the whole trajectory, actually X is also not completely known. And the idea of the approach we are doing with Maxim is to say that X here is also unknown and it's kind of nuisance parameter, functional nuisance parameter.
But what is known?
No, you have some data, noisy data, integral of x, something like this. Or discrete data with noise, and so somehow you have dynamics. So this is put in the framework of hidden Markov chains, but somehow it's similar to what is here. And the idea is, if x is fixed, then it becomes somehow the. So if you look not the difference but increments with noise, then it becomes usual regression properties. If x is known. Delta x that with noise. Then you have with respect to a usual regression problem, and then the solution, maximum likelihood estimate of a will be exactly the maximum likelihood estimate. So I mean, if you change completely the model, you don't change the estimate, but the nature will be different. And what we are doing, we try to treat it the nuisance parameter, but you cannot estimate it because it's functional. You need to project or regularize, exactly as Peter said. And if you do regularization, it seems to be possible. So I mean, you say so you don't observe x, but you assume that the trajectory of x is somehow regular. And we are doing it by putting some kind of Gaussian priors, which are functional. So x is not ground in motion, but x is a kind of smooth Gaussian process with some regularity. And under certain regularity, it becomes very stable. So it's another way to regularize it, but the problem is then the point of the bias. I'm curious about putting rough paths. It's also a way of regularization. Any regularization introduces some bias. So is it somehow studied, the bias induced by rough passes?
I'm not sure if we can see this rough path way as a regularization. I mean, in some, yeah. I mean, because we take additional information.
It's also regularization. Taking additional information is also regularization.
No,
You assume additional information, you don't have it.
My point is...
That's a tiny point of all rough path analysis.
This is part of all statistics.
No. This was no pun intended. Seriously, it's just that you are regular once you have the second order integrals, and to obtain them, you induce, I don't know, measurement bias or you misstructure information. So then this is where you drag along some error.
I am very pragmatic. Now I play a crazy guy. I am just engineer. So I am doing maximum likelihood estimator. That's what it is all about. And this maximum likelihood, doesn't matter which theory you use, you end up with the same maximum likelihood estimator, more or less. And then it appears to be unstable. Then you try to do it a little bit more stable, and you do some manipulation, and it's exactly the question. It could not be that there is in the observation process it is given. It is done. It's from the nature. And now your manipulation comes from you, and either it's reasonable or not. But it's reasonable anyway. Any reasonable way should give the same answer. So I mean, all reasonable ways should be somehow coherent, or at least neighbor. Should be some relations.
So I mean, I don't know whether this is the point, but somehow I think when you have a geometric rough path, it's the limit of a modified version of your path that you start. I mean, of your path that you started from, and of course, limit on the path level and on the value of the iterated integral. So in that sense, I guess you could say you go from a path to a, say, piecewise linear or piecewise smooth path, and use this as a proxy. And that's also, I guess, the reason why Stratonovich is the relevant notion of an integral here. But I don't think that this was really
But the geometric rough path construction is stable again. So if you have your original path,
If your
if you
original
want to have to
path,
construct a geometric rough path, then this procedure is stable. It doesn't depend on how you do it.
well, yes, but
I mean-
but keep in mind that the rough path is always a path plus the iterated integral, right? So in some sense, I'm not solving this problem that I don't have the iterated integral.
Mhm.
So I mean, the point is that this lifting map, this is not continuous. So it's shifting the problem from the estimation map to this lift. Okay, this is why you need the iterated integrals in order to obtain the stability. So,
But still, if you have a nice rough path, namely such a geometric rough path, it is the limit of a smooth path. And for a smooth path, you can construct the iterated integral from the path, of course.
And this would be a regularization because
This-
you stop at some point.
I guess you could consider as a regularization. The problem is if you have not started out from a geometric rough path,
Then you get the nice bias that you have.
then you have
regularizing
the
as not so
well, yes, which Hilmar described as the discontinuity.
It should be explored in more detail, or is it explored somehow?
I would guess that it is explored to some extent
you
because
mean the convergence of this homogeneity.
No, maybe I suggest now it's a good point of
Just some sorry, quick comment. Maybe it's reasonable to compare your estimator with recent work of Zetinov and Shiryaev, where they formulate optimal stopping problem to estimate trend in the presence of fractional moments. So I can give you a link to that paper.
Okay, so I suggest we have a thank both speakers.